Hi everyone, this video is about something called the product rule, which is a shortcut to take the derivative of certain types of functions. The proof of the product rule is not going to be on the video. I'll include it in the note, but not in the video itself. That way you don't have to fast forward it. It's not going to be tested, so it's optional to look at. After that, we'll go through some examples of the product rule. So the product rule states if we have two functions f of x and g of x and they're multiplied together, so product is another name for multiplication, the product of functions is a multiplication of functions, then the derivative of that product of f times g is not equal to the derivative of f multiplied by the derivative of g. Instead, it's equal to f times the derivative of g plus g times the derivative of f. There's different notations for derivatives, thus there's different notations for the product rule. If h of x is defined as f of x times g of x, then we could say that h prime is f of x times g prime of x plus g of x times f prime of x. Or another notation is if we, instead of writing the first function as f of x and the second function as g of x, because they may not have labels, we may have to impose our own labels on these things. If we instead label these as the first function being a and the second function being b, then the product rule in that language would read a times b prime plus b times a prime. It's the first function times the derivative of the second plus the second function times the derivative of the first. Now, order of multiplication does not matter, so we could put b prime a plus a prime b, and order of addition does not matter, so we could swap the order in which those terms appear in that expression at the end, in that addition. What's important is that there's two pieces. Each piece contains a and b, or f and g, and one of those pieces has its derivative taken. That's what's important for the product rule. Which of these notations you use does not matter. The most common error made when you just start learning the product rule is to misuse it. It's to think that the derivative of f times g is f prime times g prime, or the derivative of a times b is a prime times b prime, because it's not. It gives the wrong answer. And in some of the following examples, I am going to show you what happens if you use the incorrect formula, and show you what happens if you use a different strategy, an alternative strategy to take the derivative that does not involve the product rule. Then we'll compare all three, and I'll show that the product rule is consistent with the alternative strategy, which matches what we were doing before. And this thing, the a prime b prime, or f prime times g prime, does not match with that alternative. Okay, first example is a very silly looking example. H of x is 2x times 3x to the power of 3. It's silly because we can simplify the function and then take the derivative the old way. But let's use the product rule and see what happens. I'm going to use the a and b labels for these, a and b. And I have a reason for that. If you start labeling these f and g, like most textbooks do, most YouTube math personalities do, what if the function is already called f? Now you have f appearing twice, and it gets super confusing. The function is not going to be called a, it's not going to be called b. So it gives you a consistent labeling that you can always use that you will not get messed up with. Also, the formula ab prime plus ba prime spells ABBA, and if you're old like me, ABBA means something. So it helps you remember it. Maybe it'll help you remember it now too. So I'll take the derivative with this ABBA rule, a times b prime plus b times a prime. That's the product rule. A common question in class, hand goes up. Yes, question. Do I need to write product rule when I use the product rule? No, you do not need to write product rule when you use the product rule. Just use the product rule. Okay, so a times b prime. So a is 2x. What is b prime? Now, I'm going to show you a weird way to do some accounting to keep track of which place did which piece come from. For the part of the expression that came from the derivative of something, I'm going to use square brackets. This is not normal math notation. This is like a special keeping track and not making mistake notation that helps you survive math courses. So the square bracket doesn't have any special math meaning here. It doesn't mean include the endpoints or anything like that. It's not like it used to mean. All it means is I'm going to keep track of which piece involves a derivative. So this piece is for b prime. It's the derivative of 3x to the power of 3. The power comes down, multiplies by the number that's already in front. So 3 times 3, 9. And the power gets reduced by 1, so 9x squared. That's a times b prime. Now we have to do the plus. And I'm going to make that plus a different color so it's easier to find for someone looking at the note later. B times a prime, so b, 3x to the power of 3. And then I'll put a square bracket here for the derivative of a. The derivative of 2x is going to be just 2. Let's simplify our final answer. Let's multiply the terms together. We have 2x times 9x squared. Multiply the 2 and the 9 together, so 18. We multiply the x and the x squared together, so x to the power of 3. Plus, we do the same thing for the next piece. The 3 and the 2 multiply together, 6, x to the power of 3. We have 18 of something plus 6 of that thing, so 24 x to the power of 3 is our final answer. I mentioned at the beginning that we have a much better way to do this. We can check our answer by using that better way. H of x is equal to, let's simplify it first, 2x times 3x to the power of 3, so 6x to the power of 4, and now take the derivative. So h prime of x is, the 4 comes down, multiplies by the 6, 24x to the power of 3. And then you're asking, okay, what gives? Why do we have this product rule when I can just do that? The answer to that question is that right now, the only functions we have are polynomials or monomials. So a being 2x and b being 3x to the power of 3, that's not always going to be the case. A might be 2x and b might be an exponential function. 5 to the power of x, or e to the power of x, or it could be a log function. So function types we're going to talk about later. The product rule is going to be extremely important when we get to those function types. Okay, now down below it also mentions what happens if we try the wrong formula. So the wrong formula applies to a prime times b prime. So I'm just going to write it down. I don't want to say h prime is equal to a times b prime because it's not. I'm just going to write a prime times b prime is equal to derivative of 2x, which is 2. So a is 2x, b is 3x to the power of 3. So 2 times 9x squared, we get 18x squared, and it's not the same as 24x to the power of 3. So we know the one on the bottom is definitely correct. It's just using exponent laws to simplify the expression. Now we're using the old rules that we already talked about to take the derivative. The fact that this a prime b prime rule does not match that means that a prime b prime rule is wrong, but our product rule, which does match it, is right. That doesn't prove it. This is not a proof. The proof is a completely different beast, but it's consistent. If you find one counterexample that doesn't match the formula, it means the formula is wrong. So we proved that the derivative is not a prime b prime, but this is not a proof that the derivative is ab prime plus ba prime. It's consistent with it, but not a proof. All right, next example. We know that we can check this, but I'm going to do it with a product rule anyway to start. So I'll call the first part a. I'll give it a name, call it a. I'll call the second part b, and we'll take the derivative using the ABBA formula. AB prime plus BA prime. This time I won't make the plus sign red. Okay, so 2x squared plus 3, that's our a, and I'm going to put a square bracket for the derivative of 3x to the power of 3. We get 9x squared plus b times a prime, so 3x to the power of 3, put that in round brackets, multiplied by the derivative of a. Put that in square brackets because it's a derivative of something. We get 4x plus 0. Derivative of 2x squared, the 2 comes down, multiplies by the 2 that's already there. We get 4, x to the power of 1. We don't need to write the 1. Then the plus 3, well, 3 is a constant. Constants don't change, so rate of change is 0. Derivatives are rates of change, so derivative is 0 too. Next, let's simplify. I'm going to multiply the 9x squared into the bracket. We get 18x squared times x squared, which is x to the power 4, plus 3 times 9x squared, so 27x squared. And then we have 3x to the 3 times 4x, so 12x to the power 4. And we can combine like terms. We can't combine the first two because they have different powers on x, but the first and the last have the same power on x. They're both x to the power 4, so we can merge those together. We have 18 of them plus 12 of them. That's a total of 30 x to the power 4 plus 27x to the power of 2. This can be factored if you wish, or left alone if you wish. I wish to not factor it. I wish to leave it alone. Let's check. All right, let's check our answer by simplifying. Simplify h of x. So h of x is equal to, we're going to expand out, multiply each of the terms in the first bracket by 3x to the power of 3. We get 2 times 3, 6, x squared times x to the 3, x to the power 5, plus 3 times 3, 9, x to the power of 3. Now we take the derivative. 5 comes down, multiplies by the 6, 30. X reduces by 1 power, 4, plus 3 comes down and multiplies by the 9, 27. X power reduces by 1, power 2. Hey, it's the same. A prime times b prime, however, is going to be 4x times 9x squared, so 36x cubed, which is completely wrong. It's not even slightly right, not even close. It's totally wrong. So we've not confirmed, but we found that the derivative from the product rule is again consistent with this simplification process that we could have done at the beginning instead of using a product rule. Okay, another example. This one's the same structure. Two things multiplied together. One of the things has two pieces in brackets. Only difference is that one of these pieces now contains a fractional power. But the product rule doesn't care. The only structural thing the product rule cares about is if you have two pieces of something multiplied together, an a and a b. And we do. We have an a being x squared and a b being 1 plus the root of x. Now, right now, this is not a very big deal to be doing these derivatives because the derivatives are relatively straightforward. Later on, when the function pieces are bigger and nastier and more horrible, you may not want to do things the way that I'm showing you here. You may want to split your calculation up into pieces. So I'm going to show you how to do that for this smaller example so it doesn't look as weird when we start doing it for the horrible examples. Okay, so taking the derivative h prime of x is a b prime plus b a prime. A is x squared. I'll leave a box for b prime. Plus b is 1 plus the root of x. And I'll leave a box for a prime. And I'm going to calculate a prime and b prime off to the side. A is equal to x squared. So a prime is equal to 2x. So I'm going to put that in the a prime spot. B is equal to 1 plus the root of x, which is 1 plus x to the power of 1/2. We have to do that in order to use our derivative law. Now we take the derivative. B prime is equal to 0, since 1 is a constant, its derivative is 0, plus 1/2 times x to the power of 1/2 minus 1. So 1/2 x to the power of 1 over 2 minus 2 over 2, which is 1/2 x to the power of negative 1/2. So that can go here, 1/2 x to the power of negative 1/2. Okay, and that's a good answer. That's the derivative. But let's simplify it. Let's play with it. See what comes out. So we have 1/2 x to the 2 plus negative 1/2. Using our laws of exponents, the powers are going to add. Plus 2x plus 2x to the 1/2 plus 1. I'll explain that a little bit better. Root x is equal to x to the 1/2, and 2x is the same thing as 2x to the power of 1. I'm going to make that a little bit neater. Square root of x is the same thing as x to the 1/2. So I use those two conversions when combining the powers. Okay, let's simplify. 2 minus 1/2 is 4 over 2 minus 1 over 2, so it's x to the power of 3 over 2 plus 2x plus 2x to the power of also 3 over 2. 1 over 2 plus 1 is 1 over 2 plus 2 over 2, so 1 plus 2 over 2, 3 over 2. Now we have 1/2 plus 2 x to the 3 over 2 plus 2x. We can add that fraction together. 1 over 2 plus 4 over 2 is 5 over 2. X to the power of 3 over 2 plus 2x. So lots of fraction work there. And I want to say I beg, but I don't know if I want to go that far. I highly recommend that you do this again on your own. So I do this calculation independently to practice all the fraction work and the subtractions and using exponent laws. It's a good question to practice those skills with. Also, I highly recommend that you check by simplifying h of x and then find h prime of x. Because when you simplify, you get x squared plus x squared times x to the 1/2, which is x to the 2 plus 1/2, which is x to the 5 over 2. Take the derivative of x to the 5 over 2, you get 5 over 2 x to the power of 5 over 2 minus 1, which is actually the term that's there. 5 over 2 x to the power of 3 over 2. Then the derivative of x squared is just the 2x. Anyway, that was too fast to write down. Do it on your own. I don't want you to copy it, I want you to do it. Alright, I'm going to pause the video and write out the proof very quickly for the product rule. And I think after that, I'll see you in the next video.